Chapter 7.3, Solving Exponential Equations. Exponential equations can be solved in two ways. We can solve them graphically by graphing the left side and the right side of the equation separately and then find the x values of the intersection points. Or we can solve them algebraically by rewriting the expression with a different base than the one given. Rewriting bases. Example, rewrite each expression as a power with a base of 2. 4 to the power of 3. 4 is 2 to the power of 2, so we can write this as 2 to the power of 2 to the power of 3. And then using exponent laws, power of a power we multiply, so this becomes 2 to the power of 2 times 3 is 6. 1 over 8. 8 is 2 to the power of 3, so we can write this as 1 over 2 to the power of 3. And then we want this in terms of base 2, so we can get rid of the fraction by moving the 2 to the power of 3 on top, which then makes the exponent a negative, so 2 to the power of negative 3. 8 to the power of 2 over 3 times the square root of 16 to the power of 3. 8 is 2 to the power of 3, so we can write that as 2 to the power of 3 to the power of 2 over 3. Square root of 16 is 4. 4 to the power of 3. Then we have power of a power, 2 to the power of 3 to the power of 2 over 3. Multiply the exponents to get 2 to the power of 6 over 3. 4 can be written as 2 to the power of 2, and then to the power of 3. We get 2 to the power of 6 divided by 3 is 2, times 2 to the power of 2 to the power of 3 is 2 to the power of 6. Then the multiplication exponent law tells us to add these exponents, so we get 2 to the power of 8. Solving equations. Step 1, make the bases the same. Step 2, drop the bases and work with the exponents. Step 3, solve algebraically. Example, solve the following equations algebraically and check your answer graphically or by subbing the solution back in. First one, 5 to the power of x plus 7 equals 5 to the power of 3x minus 11. Because we have the same base, that means the exponents would have to be equal in order for the two sides to be equal. So we can just get rid of the base and look at the exponent. We would have x plus 7 has to equal 3x minus 11. This is a linear expression, so we want to move the x's to one side, the non-x's to the other side. I'm going to subtract x from both sides to put the x's on the right and add 11 to both sides to put the constant terms on the left. Then I get 7 plus 11 is 18 equals 3x minus x is 2x. Then divide both sides by 2 and we get x equals 9. Then we need to verify. Let's verify this one algebraically. Five to the power of 9 plus 7 equals 5 to the power of 3 times 9 minus 11. On the left side, we get 5 to the power of 16. On the right side, we get 5 to the power of 27 minus 11. Then that's 5 to the power of 16 equals 27 minus 11 is 16, so 5 to the power of 16. Left side equals the right side, so that's verified. 9 to the power of 4x equals 27 to the power of x minus 1. Our bases are not the same. We have 9 and 27, but we can write both of those as powers of 3, so let's do that. 9 is 3 to the power of 2, and then to the power of 4x. 27 is 3 to the power of 3, and then to the power of x minus 1. Then simplify, we have 3 to the power of 2 times 4x, which is 8x, so 3 to the power of 8x, equals 3 to the power of 3 times x minus 1. So we need to distribute the 3 into the binomial. We get 3 to the power of 3x minus 3. Now we have the same base, so our exponents would have to be equal for the two sides to be equal. So we get 8x equals 3x minus 3. Subtract 3x from both sides. That gives us 5x equals negative 3. Then divide by 5. We get x equals negative 3 over 5. Let's verify. 9 to the power of 4x, so 4 times negative 3 over 5, equals 27 to the power of x, which is negative 3 over 5 minus 1. That gives us 9 to the power of negative 12 over 5 equals 27 to the power of negative 3 over 5 minus 5 over 5, which gives us 9 to the power of negative 12 over 5 equals 27 to the power of negative 8 over 5. Let's make our bases the same. 9 is 3 squared, so 3 squared to the power of negative 12 over 5. 27 is 3 cubed to the power of negative 8 over 5. Then that simplifies to 3 to the power of negative 24 over 5 is equal to 3 to the power of negative 24 over 5. Left side equals the right side, so we've verified it. 9 to the power of 2x minus 1 equals 81 to the power of 4 times 27 to the power of x. We don't have the same base, but again, we can make the same base. All of these are powers of 3. So 9 is 3 squared, and then to the power of 2x minus 1 equals 81 is 3 to the power of 4, and then to the power of 4. And 27 is 3 to the power of 3, and then to the power of x. Simplify, we get 3 to the power of 2 times 2x is 4x, and 2 times negative 1 is negative 2. I have to distribute that 2 to the binomial. Then we have 3 to the power of 4 times 4, which is 16, times 3 to the power of 3x. Then we get 3 to the power of 4x minus 2 equals 3 to the power of 16 times 3 to the power of 3x. We add those exponents, so 3 to the power of 16 plus 3x. Now we can drop the bases since we have the same base on each side and just look at the exponents. 4x minus 2 has to equal 16 plus 3x. Again, it's linear, so move your x's to one side, your constants to the other. I'm going to subtract 3x from both sides to move my x's to the left, and add 2 to both sides to move my constants to the right. 4x minus 3x is 1x, equals 16 plus 2 is 18. Let's verify algebraically. I'm going to start here where I have the same base. I've got 3 to the power of 4 times 18 minus 2 is equal to 3 to the power of 16 plus 3 times 18. Gonna need my calculator for this one. 4 times 18 minus 2 is 70, so 3 to the power of 70 on the left. On the right, we have 3 to the power of 16 plus 3 times 18, which is also 70. So left side equals right side. Therefore, x equals 18 is a solution. Eight to the power of x plus 3 over 16 to the power of 2x minus 4 equals 32 to the power of x plus 5. Again, we don't have the same base, but we can write these all as the same base. These are all powers of 2. 8 is 2 to the power of 3, and then to the power of x plus 3 over 16 is 2 to the power of 4, then to the power of 2x minus 4 equals 32 is 2 to the power of 5, and then to the power of x plus 5. We want to simplify, so multiply 3 into this binomial. We get 2 to the power of 3x plus 9 over, multiply the 4 into this binomial, 2 to the power of 8x minus 16 equals, multiply this 5 to this binomial, 2 to the power of 5x plus 25. We're dividing the same base, so exponent laws tell us we're subtracting the exponents. We get 2 to the power of 3x plus 9 minus the bottom exponent, which is 8x minus 16, equals 2 to the power of 5x plus 25. Now we have the same base and just one of each base, so we can ignore the bases and just focus on the exponents. We can multiply this negative into the brackets. We get 3x plus 9 minus 8x plus 16 equals 5x plus 25. Combine like terms on the left, we get negative 5x, and then 9 plus 16 is plus 25 equals 5x plus 25. Move your x's to one side, your constants to the other. I'm going to add 5x to move the x's to the right side, and subtract 25 to move the constant to the left. I end up with 0 on the left and 10x on the right. Divide by 10, and I get x is equal to 0. Let's verify our solution. For my verifying, I'm going to start with 2 to the power of this exponent is equal to 2 to the power of this exponent. So I have 2 to the power of negative 5 times 0 plus 25 is equal to 2 to the power of 5 times 0 plus 25. Those terms are 0. We get 2 to the power of 25 equals 2 to the power of 25. So left side equals right side, then x equals 0 as a solution. 5 to the power of x plus 3 equals 1. Recall that any non-zero number to the power of 0 equals 1, so we can write 1 as 5 to the power of 0. 5 to the power of x plus 3 equals 5 to the power of 0. Then we can drop the bases and just look at the exponents. X plus 3 equals 0. Subtract 3 from both sides, we get x equals negative 3. Let's verify this one graphically. Enter the left side, 5 to the power of x plus 3. And then the right side is y2, just 1. Graph that. Find the intersection point. Second trace, number 5. Enter, enter, enter. And it tells us that the intersection point is when x equals -3. We could also show this algebraically. 5 to the power of -3 plus 3 equals 1. 5 to the power of 0 equals 1. 5 to the power of 0 is 1 equals 1. Note, if you are unable to rewrite the exponential expression in your equation to have the same base, then you can only solve graphically, which may give less accurate answers. We will learn how to solve these types of equations using logarithms in Chapter 8. Example: cesium-144 has a half-life of 282 days. Half-life is the length of time it takes for the substance to decay to half of its original amount. Part A. Write an exponential equation to model the amount of cesium-144 remaining. So the amount of cesium remaining after t days would be the function a of t, which equals the initial amount of cesium-144, which we don't know what that is, so we're going to call that a sub 0, then times the growth rate, or the decay rate in this case, which is 1/2 because we're talking about the half-life, then to the power of t, the number of days, divided by the time it takes for the substance to decay to half its original amount, which was 282. So there's our equation. A of t equals a0, the initial amount, times 1/2 for half-life to the power of t divided by 282, which is the number of days that have passed, divided by the time it takes for the half-life. Part B. After how long should only 25% of the cesium-144 be present? 25% as a decimal is 0.25. We don't know an initial amount, but we could say the initial amount is 100%, which is 1 as a decimal. So we want the amount remaining, which is a of t, to be 0.25. If the initial amount is 1, and our function is 1 times 1/2 to the power of t over 282. So we want to try to write the same base on each side. 0.25 is 1/4, which equals 1/2 to the power of t over 282. I can write 4 as 2 to the power of 2, so 1/4 can be written as 1 over 2 to the 2 equals 1 over 2 to the power of t over 282. Then the first fraction, 1 over 2 to the power of 2, I can write as 1 over 2 brackets to the power of 2 equals 1 over 2 to the power of t over 282. Now I can ignore the bases and just focus on the exponents. We have 2 equals t over 282. Multiply both sides by 282. 282 divides out on the right side, on the left side. we have 282 times 2 gives us 564. So t equals 564. And that is days. Then we can say after 564 days, only 25% of the cesium-144 will be present. Example, a bacteria culture starts with 5,000 bacteria. After 5 hours, the estimated count is 40,000. What is the doubling period for the bacteria? So we can write an equation. A of T, so the amount of bacteria, would equal A0, the initial amount, times 2, because we're doubling, to the power of T divided by D, which is the time it takes to double. So we can see that this is essentially the same equation as this, except that here we are doing the half-life, so we have a base of 1/2, and here we're doubling, so we have a base of 2. This is our time to double. This was our time to half. This is our initial amount. This is our initial amount. This is the amount after T hours. This is the amount after T hours. So all of these types of word problems are set up with similar equations. Then we can plug in our information. The estimated count is 40,000. That would be our amount that we have, so AT. In this case, that's after 5 hours, so that's A5, which means our T value is 5. We start with 5,000 bacteria, so we have an A0 of 5,000. So then we can write the equation 40,000 equals 5,000 times 2 to the power of 5 divided by D. What is the doubling period? The D value is what we're trying to determine. We can divide both sides by 5,000. We get 8 equals 2 to the power of 5 over D. We can write 8 as 2 to the power of 3 equals 2 to the power of 5 divided by D. Then we can drop the bases, and we have 3 equals 5 divided by D. Multiply D to both sides. We get 3D equals 5. These D's divide out. And then divide both sides by 3. And we get D equals 5 over 3. Our time was in terms of hours. It says after 5 hours. So our D value is in terms of hours. Then we can say the doubling period for the bacteria is 5/3 of an hour. Compound interest. Compound interest is interest that is calculated and added to an amount at a certain time, and then the interest after that point is calculated on the new total. So the principal plus the interest that's been added. So compound interest is a good thing for investing because you start making money on money you've made before, since your interest gets added to your principal, and then the next term's interest is calculated based on the new amount. Compound interest is a bad thing for debt for that exact same reason. You end up paying interest on your interest. So some terminology. Interest is compound at different times. We have annually, which is 1 time a year. Semi-annually means 2 times a year. Quarterly, there's 4 quarters in a whole, so that means 4 times a year. Monthly, there's 12 months in a year, so that means 12 times a year. Bi-weekly, there are 52 weeks in a year, so bi-weekly is every second week, which is 26 times in a year. Weekly is 52 because there's 52 weeks in a year, and daily is 365 because there's 365 days in a year. We don't really worry about leap years unless the question said it's a leap year. So in our compound interest formula, we have a variable I. That equals the interest rate in decimal form divided by the number of compounding periods. Number of compounding periods are those numbers that we just wrote down. The formula that we will use for these types of questions is A equals P times 1 plus I to the power of n, where n is the total number of interest periods. This is the number of years times the periods per year. So number of years times whichever one of these numbers fits for the question. A is the total amount, which is the initial or the principal plus the interest. P is the principal amount, which is the initial amount either invested or borrowed. I is the interest rate per compounding period. As we said over here, you get that by taking the interest rate as a decimal and dividing it by the number of compounding periods. And n is the total number of interest periods. I don't know why n is stated twice, but that's okay. It's important. Total number of interest periods, so number of years times periods per year. Example, determine how long $1,000 needs to be invested in an account that earns 8.3% compounded semi-annually before it increases in value to $1,490. So $1,000, how long does $1,000 need to be invested? $1,000 would be our principal amount or our initial amount that's invested. The account earns 8.3% as a decimal, that is 0.083. It's compounded semi-annually, which means 2 times a year. And we want to know how long will it take to increase in value to $1,490. Our formula is A equals P times 1 plus I to the power of n. Our A is the total amount, which is the $1,490. So we have $1,490 equals our principal amount was 1,000 times 1 plus I we can calculate because we have the interest rate as a decimal and we have the number of compounding periods. So I is 0.083 divided by 2. 0.083 divided 2 is 0.0415. Sub that into our equation, 0.0415, and then to the power of n, which is the thing we're trying to find because it says determine how long it needs to be invested. I can simplify this. I can divide both sides by 1,000. Then I get 1.49 equals 1 plus 0.0415 to the power of n. I'm not going to be able to write this with the same base, so I can't solve it yet because we are going to learn how to do that in Chapter 8. So then I have to solve graphically by graphing one side as y1 and one side as y2, and then finding the x value of the intersection point. So left side is 1.49, right side is bracket 1 plus 0.0415, close bracket, to the power of n, or x in this case. Graph that. We want to see the intersection point, second trace number 5, enter, 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 and it says that it is at 9.8. So the x value of the intersection point is 9.8. So that tells us that n equals 9.8. And if we look back to our definitions, n is the total number of interest periods, which is the number of years times the periods per year. N equals number of years times number of compounding periods per year. So in this question, we compounded semi-annually, so 2 times a year. Then our n value of 9.8 equals our number of years times 2. So to solve for the number of years, we would divide both sides by 2. 9.8 divided by 2 is 4.9. Then we can say it will take approximately 4.9 years for the investment to reach $1,490. That brings us to the end of the Chapter 7 notes.